Hello everyone, welcome to the lecture again. In the last class, we discussed about the simple harmonic motion. Today, we are going to solve couple of examples. But before that, let me summarize the result of the previous class. So, simple harmonic motion okay. In general, we have a mass which is attached to a spring, and to set up the motion you displace it by applying a force F, and then the mass m makes an oscillatory motion about the equilibrium position. So, the equation of motion of the mass m was m x double dot equal to minus k x. Then we define a quantity omega equal to square root k by m. Then the equation becomes x double dot equal to minus omega square x. We saw that this equation has the solution, and the solution can be x equal to a cos omega t plus b sin omega t. The solution can also be written as x equal to c sin omega t plus phi, and here a and b and c and phi, they are related. The time period of this motion t was 2 pi square root m by k, and the potential energy was half k x square. Okay. Now, we also saw that the velocity at a distance x from the equilibrium position is v equal to omega square root a square minus x square, and therefore, the kinetic energy was half k a square minus x square. Now, since the potential energy is this and the kinetic energy is that, therefore, the total energy was half k a square, and this was independent of x. Okay. Now, let us look at one example. A particle is moving with simple harmonic motion in a straight line. When the distance of the particle from the equilibrium position has the values x1 and x2, the corresponding value of the velocity are u1 and u2. Okay. Find the time period. Okay. So, we already saw that when a particle is at a distance x from the equilibrium, in that case the velocity u is equal to omega square root a square minus x square. Herein it is given that when the particle is at a distance x1, its velocity is u1. So, therefore, u1 equal to omega is square root a square minus x1 square. Okay. And here a is the maximum distance that the particle can go. Okay. And similarly, you have u2 equal to omega square root a square minus x2 square. So, therefore, from here we can find out the value of omega. Okay. For that, let us do u1 square minus u2 square. So, that will be equal to omega square x2 square minus x1 square. Okay. Or the value of omega is equal to u1 square minus u2 square divided by x2 square minus x1 square square root, and we already know the time period in terms of omega. Time period t is 2 pi by omega. So, therefore, it will be 2 pi square root x2 square minus x1 square over u1 square minus u2 square. Now, let us discuss the springs which are connected in series and parallel. So, the first one is the spring connected in series. So, let us say we have the following situation. We have a spring, then another spring, and then another spring, and a force F is applied. So, when the force F is applied, all the springs are going to experience an extension. Let us say the first spring experience an extension of x1, second one x2, and the third one x3. Okay. So, as I said, if an external force F is applied, then the force exerted on each spring will be the same. So, here the force F is acting, so that F will give you an extension. So, that will be determined by K1 x1. Similarly, F will be K2 x2, and here F will be K3 x3, where K1, K2 and K3 are the spring constant of spring 1, 2 and 3. Okay. So, from here you can see that x1 will be F over K1 and x2 will be F over K2 and x3 will be F over K3 and so on. Okay. Now, let us say the whole spring system behaves as a single one. Okay. With, let us say, a spring constant K. Okay. So, in that case, so you can see from the figure that the total deformation, okay, will be x1 plus x2 plus x3. So, x will be x1 plus x2 plus x3. Now, since the whole system we said is behaving as a single spring, so therefore, x will be F over K, and x1 we have already determined, it is F over K1 plus F over K2 plus F over K3. Now, F will get cancelled, therefore, the equivalent spring constant will be 1 over k equal to 1 over k1 plus 1 over k2 plus 1 over k3 dot dot dot. Okay. So, this is the case wherein the springs are connected in series. Now, let us see the case where a spring are connected in parallel. Okay. So, here in the situation is like that, you have let us say 3 springs and on these springs the force F is applied. Okay. So, if we apply a force F, then each spring will be stretched by the same amount. Okay. And let us say that amount is x. So, because of this force F, the spring get extended by x. So, therefore, for the first spring the force F1 will be k1 times x, and for the second spring F2 will be k2 times x, and for the third spring it will be k3 times x. Okay. And total force F will be F1 plus F2 plus F3. So, F is equal to kx, wherein again we have said that let us say the whole system behaves like a single spring of spring constant k, then F equal to kx, and this will be k1x plus k2x plus k3x, and from here we get k equal to k1 plus k2 plus k3 plus dot 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 if there are other springs. So, this is the effective spring constant when the springs are connected in parallel. Now, let us look at another problem statement. Two springs S1 and S2 are connected to a mass m as shown in A, B and C. If the spring constant are k1 and k2, find the expression for time period in the 3 cases. In the first case, you can see that the springs are connected in series. So, therefore, the spring constant k will be 1 over k equal to 1 over k1 plus 1 over k2, because the spring are in series. Okay. So, therefore, 1 over k will be k1 plus k2 divided by k1 k2, and therefore, k will be k1 k2 divided by k1 plus k2, and we know that the time period t is equal to 2 pi square root m over k. So, therefore, t will be 2 pi square root m into k1 plus k2 divided by k1 k2. Okay. In the second case, the springs are connected in parallel. So, therefore, k will be k1 plus k2, because the springs are in parallel. So, therefore, T will be again 2 pi square root m over k, and k is k1 plus k2. Now, let us look at C. So, here if one spring will get stretched, then the other spring will get compressed. So, you can clearly see that if one spring will stretch, then the other spring will get compressed. Okay. Therefore, both the spring will exert the force in the same direction. Okay. And the total force F will be F1 plus F2, wherein F1 is the force by the first spring and F2 is the force by the second spring. So, F is equal to Kx. So, this is the effective K equal to K1x plus K2x, and therefore, K equal to K1 plus K2. So, this is same as the parallel case. Therefore, T will again be 2 pi square root m over k, where k is K1 plus K2. Now, let us look at two body harmonic oscillator. Okay. So, let us say I have two masses m1 and m2 and they are attached by an spring. Okay. To formulate the problem, let us say that the first mass is at a distance x1 and the second mass is at a distance x2, and the natural length of the spring is L. Okay. Now, to set up the motion, you stretch the spring. Therefore, let us say on the mass m1, the force F is acting in that direction, then the force on the second mass will act in this direction. Okay. So, the extension of the spring, which is x, will be x2 minus x1 minus its natural length L. Okay. Now, for the first mass, the equation of motion is m1 x1 double dot is equal to kx, and for the second mass m2 x2 double dot is equal to minus kx. Okay. Because the forces are acting in opposite direction. Okay. Let us say this is equation 1 and this is equation 2, then we can combine this equation. If we multiply equation number 1 by m2 and equation number 2 by m1 and subtract them, then we have m1 m2 d2 over dt square x1 minus x2 equal to kx m2 plus m1, or I can rewrite this as m1 m2 over m1 plus m2 d2 over dt square x2 minus x1 equal to minus kx. Okay. Let us define this quantity m1 m2 over m1 plus m2 as mu which is called the reduced mass of the system. It is called reduced mass because the value of mu will be smaller than either m1 or m2, and we have this quantity d2 over dt square x2 minus x1 that can be written as d2 over dt square x2 minus x1 minus L, because this L is constant. Okay. And from here this is nothing but x. So, therefore, it can be written as d2 over dt square of x. So, therefore, the above equation becomes mu times d2x over dt square equal to minus kx. So, this equation you can see that it is identical to the single harmonic oscillator. Let me write it down. This is identical to the single body harmonic oscillator. The only difference is your m is getting replaced by mu, and x here is the relative displacement of the two masses from the equilibrium. Okay. Therefore, the time period or the time period of the oscillation t will be t equal to 2 pi square root, instead of m we have mu divided by k. Now, let us discuss simple pendulum, which is also an example of simple harmonic motion. So, in simple pendulum you have a heavy mass, point like mass, which is suspended with an string, and then the motion is set up by displacing it slightly. Okay. So, you have a heavy particle or the point mass suspended from an inextensible weightless string whose one end is fixed. Okay. So, let us say this is the string, and you have the weight which is suspended through it, and then the motion is set up by displacing it little bit, let us say by an amount x. Let us say the length of the string is L and this angle is theta. See? So, theta is small, then the mass of the particle mg or the weight of the particle is going to act downward. Since that angle is theta, this angle will also be theta. The tension T is going to act upward, and the restoring force is going to act, which will be perpendicular to the string. So, you can see from the figure that T is equal to mg cos theta, and the maximum value of cos theta can be 1. Therefore, T max or the maximum tension in the string will be mg, and this is the case when theta is 0 degree. Okay. So, that means when the particle is over here, then the tension in the string will be the maxima. Now, let us say this is the positive x direction. Now, the force F will be minus mg sin theta, and since theta is small, therefore, sin theta is theta, and you can see from the geometry that sin theta is x over L, therefore, theta is x over L. Okay. So, I can write down F equal to minus mg theta, or F equal to minus mg theta is x over L. So, here this is in the form of F equal to minus kx, where this k is mg over L. Therefore, the simple pendulum is a simple harmonic oscillator. Because it is in the form of F equal to minus kx. Now, we know for the simple harmonic oscillator, the time period t is 2 pi square root m over k. Now, let us put the value of k, 2 pi square root m over k. K is mg over L. Okay. So, m will get cancelled, you get t equal to 2 pi square root L over g, which is very famous result. So, time period is independent from the mass of the particle. With this, let me stop here. See you in the next class. Thank you.